Hi, welcome back to part 2 of the sec of concavity. Remember what we're looking for is we are looking for where the function changes concavity, something called a possible point of inflection. And we saw that in our graph in video part 1. So for part 2, we already did number 1 on another video here. So on my other video, so take a look at that if you need to. So for question number 2, we have to take the derivatives. We have to remember for concavity, we have to look at the second derivative. So my first derivative, I am going to use quotient rule. You can use product rule for this one. It's actually kind of easy for this one. But I like to use quotient rule because it's good practice. So it's the bottom times the derivative of the top, which is 0, minus the top times the derivative of the bottom, all over the bottom squared. Now if you simplify that, that becomes negative 12x over x squared plus 3 squared. Taking the second derivative, it's a little bit nastier, but I'm still going to use quotient rule, low, which is going to be x squared plus 3 squared times the derivative of the top, which is negative 12. Minus the top, which is this, becomes plus 12x, times the derivative of the bottom, chain rule, 2 times x squared plus 3 to the 1, don't forget the inside, 2x, all over that bottom squared. Now this looks really nasty, and if you try to distribute this, it is pretty nasty. But I can use a little bit of algebra. I actually have 3 terms here, this term, this super long term, and this term on bottom. And if you notice, they all have this x squared plus 3. So I can cancel them out. Matter of fact, this just goes away entirely. That means 3, and this becomes only 1. And I can simplify this using a little bit of algebra. The bottom stays x squared plus 3 cubed, but the top, if I distribute, we get negative 12x squared minus 36 plus, that becomes 24 times 2x, or 48x squared, which is 36x squared minus 36, divided by x squared plus 3 cubed. Now we have to find those possible points of inflection, PPOI. Remember, we are looking for changes in concavity. In other words, where does the slope go from opening down to opening up? That meeting point right here, like my thumb and my finger there, it's that meeting point. Where they meet is that where that concavity changes, and we call that a possible point of inflection. We'll talk why it's possible in just a few moments. Now, to get those, it's the same as our first derivative test. We set the second derivative to 0, or see where the second derivative does not exist. Equal to 0. Thank you, Leibniz. Let's just look at the numerator. And set the bottom equal to 0. Again, we don't really care about the cubes, just the x cubed squared plus 3 equal to 0. Try solving the second one. We get this, negative 3. We take the square root of negative 3, and that's not going to happen for us. That's imaginary. Over here, if you're good at the algebra, remember that's just plus or minus 1. So these are my possible points of inflection. To determine that, I look at their second derivative. I use my second derivative test. I'm at negative 1 and 1. Remember, we're going to plug our values, our choices, into that second derivative. So if I pick something less than negative 1, like negative 2, this becomes 36 times 4 minus 36, which is positive, over the bottom is always positive as well. So this is positive, so we know that this is concave up. Remember, we're looking at concavity. Don't draw an arrow. We're looking for that concavity. In the middle, I'll pick 0, pretty easy. I get 0 minus 36, so the top is negative. The bottom's always going to be positive. That's negative, so this is concave down. And if I pick x equals, let's say, 3, I would get 9 times 36, which would be way bigger than 36. So the top here is going to be positive, and again, the bottom's always positive as well. So it's concave up. So now I can look at my answer, get my answer. Ready? The function is concave up on the interval negative infinity to negative 1, or 1 to infinity. And that is because, just like the first derivative test, but this time our second derivative is positive. We are concave down on the domain in the middle, where it's negative. It's going down, like a disco clown. Negative 1 to 1, and that is because the second derivative is less than 0. Now, if you notice, at negative 1, we go from concave up to concave down, right there. So we have a point of inflection at negative 1. Also at 1, we have another one, concave down, and afterwards concave up. So we actually have 2 points of inflection, POIs, at x equals plus or minus 1. And the reason they're points of inflection is because they are changing signs. Because the second derivative changes signs. And that's how we get those points of inflection right there. Okay, so let's go ahead and, let's see here. Let's go ahead and take a look at another example. Oh no, this one's going to get ugly. I'm sorry, this one is going to hurt. Alright, so we have x times the square root of x plus 1. So if I write this, this becomes x times x plus 1 to the 1/2. I am going to use my product rule here. The first times the derivative of the second, so x times 1/2, x plus 1 to the negative 3/2, times 1 is a chain rule, but it's just 1 on the inside, plus the second, x plus 1 to the 1/2. Now that's my first derivative. Okay, now is where the fun actually begins. Okay, because now we have to take the second derivative. And this one is not very fun to do. So, whoops, that should be a negative 1/2 there. Sorry about that. Don't tell my students I made that mistake. That should be a negative 1/2. So when we take the second derivative, I'm not going to clean this up yet. I have product rule here. A first, and there's my second. So my first is just going to be x. The derivative of my second becomes negative 1/4 x plus 1 to the negative 3/2 plus the second, which is 1/2 x plus 1 to the negative 1/2 times the derivative of the first. Plus, now we're going to take the derivative of this, 1/2 x plus 1 to the negative 1/2. UGLY, that don't need no alibi. It's ugly. Yes, yes, it's ugly. But I can clean up a little bit. For example, I can add these two together. That's just, I got 1/2 plus 1/2, that's just 1. This, and I'm also going to start writing them as a fraction. Over here, we're going to get negative x over 4 times x plus 1 to the 3/2. Plus, this is 1 over x plus 1 to the 1/2. If I were to combine those two, that's what that would become right there. I am going to now combine these to a single fraction. My common denominator, of course, being the 4 x plus 1 to the 3/2. Now this x has it all, but the 1, it needs the 4, and take a look here, it has x plus 1 to the 1/2, it needs x plus 1 to the 3/2. I need to add a whole x plus 1 to it, and that would be our answer there. Cleaning this up a little bit, this becomes negative x plus 4x, so we get 3x plus 4, and in the denominator, 4 times x plus 1 to the 3/2, and there is our second derivative. Ooh, do this one 2 or 3 times, become an expert at that one, I tell you. But now we're ready for our possible points of inflection. BPOI. Papoi, papoi. Right? Where does the second derivative equal 0? Where does the second derivative not exist? Well, where does it equal 0? Again, thank you, Leibniz. He said, just look at the top of the function. Or however Germans speak, I don't know. So we get x equals negative 4/3. But we're going to come back to this in a second. Where does this not exist? I only have to worry about the x plus 1 equals to 0, so I get x equals negative 1. Now, there is something going on here. If we go way back up here to the original equation, if you notice, we have this x plus 1, but it's under a radical. This tells me we have a domain restriction. Remember all those from pre-cal? This is saying x has to be greater than or equal to -1. So when I go down here, this x equals -4/3, that's less than -1. So we don't have to worry about this one. This is out of the domain. Now, x equals -1 will work, so we can include that. So when I do my sign chart, I have -1. It's the only one possible. F double prime and F. Now, I'm not going to worry about anything over here. Anything to the left of -1 won't work. I mean, you can try it. Plug in -3. You will get -2, but you're taking an even root of it. It won't work. So anything over here is out of the domain. We have an even root. So nothing below -1 will work because it's outside my domain restriction. So I'm only going to check a number bigger than -1. X equals 0. And if I plug 0, remember I'm plugging into my original function. That's what I'm plugging it into. Not my original, I'm sorry, my second derivative. I'm going to get a +4 over, and the bottom is also going to be positive. So this is concave up. So we would say the function is concave up on the domain -1 to infinity, and that is because the second derivative is greater than 0. So this function is always concave up, right here. There are no points of inflection, and that is because there is no sign change in the second derivative. So there's no point of inflection there. All right, go to part 3. I have 2 more examples with you, a trig function and the other one. I'll see you then.